Hi, in this talk I present our work, Sign Language Segmentation with Temporal Convolutional Networks. My name is Katrin, and this work was done in collaboration with Nicolaj Stache, Albanie and Gül Varol. The task of this work is automatically segment sign language videos. For this we use videos of continuous sign language as input. In these videos we want to detect boundary and sign segments, where a boundary represents the start and end time of each sign. Why do we need sign segmentation? One motivation is to speed and scale up sign language data collection. To get an idea of this, for a 1-hour video, a professional BSL annotator needs about 100 hours to annotate this. From this 100 hours, approximately 25 to 50 hours are spent for the segmentation part. So if we could automatically segment the signs, we could improve the data collection process. A second motivation are automatic tools for linguistic analysis. Here you can see an example tool with a continuous sign language video, where we can import the automatic generated segments. This can be used to obtain statistics about the sign durations, and with this the signing speed, or the number of signs in a given interval. The challenges which occur in this task are first, the fact that sign languages convey meaning through multiple channels. This includes the hand pose, location in space, and the hand movements, as well as facial expressions or head and body movements, as you can see here in the video. The second challenge are co-articulation effects. Since we work with continuous signing, the appearance of a sign is influenced by the previous and next sign. This is in contrast to isolated signing. The last point is about the visual appearance in our dataset. Here you can see the differences in the background and the signer pose. For fast movements, we can see here that motion blur occurs around the hands. An additional point are the occlusion of parts of the body. On the left image, parts of the face, and on the right, a part of the right hand are occluded. In this work, we use 3 different sign language datasets. BSL corpus is our main dataset. In this corpus, clause annotations are only available for a subset of the video. We mainly use this data to train our models. The second dataset, BSL1K, is also a British Sign Language dataset. We manually annotated a small portion of this to test the generalization ability of our model. The Phoenix Weather 2014 dataset is our last one, which is a German sign language dataset for which automatic generated labels are available. This dataset is mainly used to test the cross-lingual generalization performance. To get the times of the sign boundaries, we propose the usage of an I3D model to get spatio-temporal features. These features are then processed with a multi-stage temporal convolutional network. In order to train the I3D model, we use a randomly chosen 16-frame input. These frames are fed into an I3D backbone which generates spatio-temporal features. A classification layer on top of this feature vector generates the sign class probabilities. During the training, we always use the label of the middle frame to calculate the loss. After this training, we only use the backbone to generate feature vectors of the whole video with a sliding window. These feature vectors are then used to train the multi-stage temporal convolutional network, or MSTCN. This is trained as a frame-level binary classification. We follow the work of Farha et al. For the training process. We now want to give some quantitative results. We first show the impact of pre-training the I3D network. We can see here that fine-tuning the I3D backbone with BSL corpus significantly improves performance. Further, we can see that pre-training with BSL1K is not necessary. We now compare the results with our re-implementation of the previous state-of-the-art, which uses geometric features and a random forest classifier. Here you can see the results on BSL corpus. This was the dataset we used for the training. A first improvement can be obtained by using the MSTCN instead of the random forest classifier. Changing the features from geometric features to spatio-temporal features obtained by the I3D, we get a further significant improvement. To test the generalization ability, we use the same model on the two other datasets. First, on BSL1K, where we can see that we are also able to outperform the state-of-the-art. And second, on the German Sign Language dataset Phoenix 14, where we can see a limited but reasonable performance. This result indicates that the model has learned some common visual cues between the languages. Here you can see some qualitative results. The video is slowed down by a factor of 6. On the bottom we show the ground truth and the predictions of our model. Here on the top you can see some other success cases for BSL corpus. Below this you can see some of the limitations of the model. This includes over-segmenting fingerspelling or abrupt changes during a sign, and under-segmenting very short signs. On the bottom we show two randomly chosen examples of BSL1K and Phoenix 14. You can find the corresponding videos on our project page. Thank you for your attention.